Uh, Anyone can hear me? Can you hear me, guys?
Yes.
We can hear you, but your voice is low.
Okay.
Yes.
What about now?
It's okay now. You can continue.
So, my friends Salman and Shahir explained beautifully the concepts of sensitivity. So, I will be carrying on the later part of the presentation. My name is Tahathar. Here is my student ID. This will, this will be my presentation flow. First of all, I will be explaining AC power flow methods, then the contingency selection, and later on I will explain concentric relaxation. AC power flow method. Like my friend Salman explained the sensitivity method, the calculation made by the network sensitivity are faster than those made by AC power flow methods, and therefore find wide use in operation control systems. However, there are many power systems where voltage magnitudes are crucial in assessing contingencies. In addition, there are some systems where VAR power flows predominates on some circuits, such as underground cables, and an analysis on only the megawatt flows will not be adequate to indicate overloads. When such situations present themselves, the network sensitivity method may not be able to fulfill our required tasks, although it is a great method, but it still lags in some areas. And the operation control system will have to incorporate a full AC power flow for the analysis of contingency. When an AC power flow is to be used to study each contingency case, the speed of solution and the number of cases to be studied are critical. If the contingency alarm comes too late for the operator to act, they are worthless. More operation control centers that use an AC power flow method use either Newton-Raphson or decoupled power flow method. These solutions are used because of their speed of solution and reliability. The decoupled load flow has further advantages than that of matrix alteration formula can be incorporated into simulation using Jacobian matrix at each iteration. This is a flowchart of simple AC power flow security analysis. Here we can see that we take uh, all possible outages that can occur, and I is equal to the one taking each outage at a time and carrying it on through the cycle until an alarm is raised, and this goes on. The simplest AC security analysis procedure consists of running an AC power flow and system analysis for each possible generator, transmission line, and transformer outage, as shown in this flowchart. This procedure will determine the overloads and voltage limit violations accurately, at least within the accuracy of power flow program, the accuracy of the model data, and the accuracy with which we have obtained the initial conditions for the power flow. But there comes the limitations with it. It does suffer major drawbacks, however, and concerns the time such a program takes to execute. As we can see here, it is taking all the possible contingencies outages list, so it will take a lot of time carrying out the operation one by one. If the list of outages have several thousand entities, then the total time to test for all the outages can be too long. We are thus confronted with a dilemma. Fast but inaccurate methods involving the A and D factors can be used to give rapid analysis of the system, but they cannot give information about mega VAR flows and voltages. Slower, full AC power flow methods give full accuracy, but unfortunately takes too much time. But fortunately, there is a way to come out of this dilemma. Because of the way the power system is designed and operated, very few outages will actually cause trouble. Therefore, we will shortlist those outages that are the main cause of any haltation of the system. That is, most of the time spent running AC power flows will go for the solution of the power models that discover that there is no problem. Only a few of the power flow solution will in fact conclude that there is an overload or voltage violation exist. In the last flowchart, there was all the possible outages we were taking into account. But here on, when we select some of the cases, we shortlist them in another list and then we carry out our operation. The solution to this dilemma is to find a way to select such contingencies in such a way that only those that are likely to result in an overload or voltage limited violation will actually be studied in detail, and the other cases will go unanalyzed. A flowchart for the process like this appear as I am showing in this flowchart, as you can all see here. We can carry on the same way as we did in the last flowchart, but in this only the thing different in this one is we are shortlisting only the voltage limit violations and overload violations. But if we do so, like shortlisting some of the violations, it gives us two sources of error. Number one, placing too many cases on shortlist. This is essentially the conservative approach and simply leads to longer run time for the security analysis procedure to execute, and making it again more time consuming than the previous one. Number two is the skipping of the cases. Here, as I have already told you, we will select only the violations of the overload and voltage. So we will be excluding some of the major problems in the from the list. So a case that would have shown a problem in not placed in the short list and result in possibly having the outage take place and cause trouble without the operator being warned. So this is also a drawback of this procedure. Coming to the contingency selection, we would like to get some measure as to how much particular outage might affect the power system. We have to calculate and we have to need some of the measuring unit for the purpose. The idea of the performance index seems to fulfill this need. The definition for the overload performance index PI is as follow. I am showing here the formula. PI is equal to sum of all branches is bracket P flow over P max power 2n. If n here that is shown in this formula is a large number, the pi will be a smaller number if we solve the equation. If all the flows are within the limits, and it will be a large if one or more lines are overloaded. The problem then is how to use this performance index. Various techniques has been tried to obtain the value of pi when a branch is taken out. These calculation can be made exactly if n is taken as only 1. That is the table of pi values. One for each line in the network can be calculated quite quickly if we choose always n equals to 1. The selection procedure then involves ordering the pi table from the largest value to the least value. The line corresponding to the top of the list are the candidates for the shortlist. However, when n is equal to 1, the pi does not snap from near 0 to near infinity as the branch exceeds its limit. Instead, it rises to a quadratic function. A line that is just below its limit contributes to pi almost as equal that is just under its limit. Thus, the pi ability to distinguish or detect the bad case limited when n is equal to 1. How ordering the pi values when n is equal to 1 usually result in the list that is not at all representative of one with a truly bad case at all. Trying to develop an algorithm that can quickly calculate pi when n is equal to 2 or larger have proven extremely difficult until now. But there is one way to solve that problem. One way to perform an outage case selection is to perform a method called 1P 1Q method. Here, a decoupled power flow solution is used. The procedure is interrupted after one iteration, 1P calculation and after 1Q calculation. That's why it's called 1P and 1Q method. With this procedure, the pi can use as a large value of n as desired. Another advantage of this method is the fact that the voltage can also be included in the power system. Thus, a different pi can be used. That the formula is shown here. As we can see, pi is equal to E sum of all branches power flow divided by power flow max 2n plus sum of all branches delta E divided by delta EI max power 2m. Here delta mod EI is the difference between the voltage magnitude at the end of the IP-IQ procedure and the base case voltage magnitude. Delta E mod max is the value set by the utility engineer, indicating how much they wish to limit a bus voltage from changing on one outage case. To complete the security analysis, the pi list is sorted so that the largest pi appear at the top. So that the largest pi value indicates the largest fault or the most severe fault in the list. The security analysis can then start by executing full power flow with the case, which is second. Which is fixed and switches which do not have any alarms, and the system runs smoothly. Coming on to the concentric relaxation. It is another idea to enter the field of security analysis in the power system. Is that an outage only has a limited geographic effect. Here, we can see that it is being dealt as an area by area solution. Like we consider layer 1, layer 0, layer 2, and so on, depending on upon the complexity of the power system. The concentric relaxation procedure was originally proposed by Zaborowski. The loss of the transmission line does not cause much effect 1,000 miles away. In fact, we might hope that it doesn't cause much trouble beyond 20 miles from the outage. Although, if the line were heavily loaded, does not cause much trouble. If the line were heavily loaded, high voltage line, its loss will most likely be felt more than 20 miles away. So realize any benefit from the limited geographical effect of the outage. The power system must be divided into two parts, affected region and unaffected region. To make this division, the buses at the end of the outage line are marked as layer 0, as I've shown in the figure. The buses are one transmission line or one transformer from layer 0 are then labeled layer 1. This same process can be carried out layer by layer until all the buses in the entire network are included. Some arbitrary number of layers is chosen, and all buses included in that layer and lower numbered layer are solved as per power flow with the outage in place. So basically here we are doing solution of the system layer by layer by solving the system layer 0, then layer 1, layer 2 until all the problem are solved in the system. The buses in the higher number layer are kept at constant voltage and phase angle. This procedure can be used in two ways. Either the solution of the layer included becomes the final solution of that case, or all overloads and voltage violations are determined for this power flow. This is showing this layering procedure as I have discussed. The concentric relaxation method can be seen as the earliest localization attempt. The main idea behind this method is to solve a small portion of the system in the vicinity of the contingency while treating the remainder of the network as infinite expands. The area to be solved is concentrically expanded until the incremental voltage changes along the last solved tier of the bus are not significantly affected by the inclusion of the additional tier of buses. So here we won't be adding any other layer until the previous problem is solved. But it also comes with our drawbacks. The method suffers from number of weaknesses. Number one is the unreliable convergence in terms of mismatches of the Gaussian-Seidel solution algorithm. Possibility of missing severe problems outside the selection portion pocket due to the use of small cutoff network and the exclusion of the boundary buses from outage severity consideration. Another problem is the lack of consistent criteria for the selection of buses to be included in small network because we don't know whether we are selecting the layer 0. So the problem is in this layer or not. So carry on this presentation. Any questions from your side?
I have a low question. Any questions from you guys or from the students? Okay. So the last event, yeah.
Hello. Can you see the slides? Hello.
Yes.
we can.
Yes,
Yes.
Nara.
Yes. My name is Naila, and I'm going to discuss about the second technique of contingency selection, which is bounding. As first technique was discussed by Taha, which is concentric relaxation. And we have trouble or problem with this technique. First technique is that it requires many layers. So this problem of concentric relaxation can be overcome by making adjustable region around the outage to solve for the overloads. So this technique is called bounding technique. And the bounding technique can be accomplished by using three flexible subsystems defined as N1, N2, and N3. N1 is basically a subsystem which immediately surround the outage where any outage occur. N2 is a external subsystem that will not be solved in detail, and N3 is a subsystem which actually separate the N1 and N2 region, and it has some set of boundary buses. So this is bounding technique, and to implement this bounding technique, so we have to make some certain assumption about the phase angle spread across the line and N region 2 with injection in N1 and the maximum phase angle appearing across any two buses in region N3. So this is the certain assumption to implement the boundary technique. Further, we'll discuss about the boundary technique. If we are given a transmission line N2 with the flow from P to Q, this is a flow from before the failure. So so there's a maximum amount that the flow can be changed, can be shift on P to Q. It can be increased or it can be decreased to its it can be increased to its upper limit or it can be decreased to its lower limit. So mathematically we can write here that maximum flow from P to Q is equal to, here we take the smaller value, which is the flow increasing minus the current flow, or current flow minus the decreasing flow. Further, we can translate this power shift is transferred into the maximum change reactance from P to Q. And in this figure, we can see three regions here, N2 where P to Q bus, and N3 we have I to J bus, and N1 region where any outage occur. This here we have K to M buses. So let's discuss about further bounding. The maximum change in the phase angle difference across PQ in N2 region, which defines an upper limit for the angle difference in region N3. Or mathematically, we can write here the difference of change in angle from P to Q is less than the difference of change of angles of I to J. Or we can replace this term change in P to Q phase angle with this term, as we have seen in the slide here. So we'll get this equation. And here I and J are any pair of buses in N3, and this right side of equation which provides an upper limit to the maximum change in angular speed across any circuit N2, and it will provide the limit to the maximum change in the flow. So now we have for completely safe region. For completely safe region where the maximum shifted phase angle difference is small enough to be less than all the bias flow limits. And mathematical representation, here we can see that this the maximum shifted phase angle difference is small enough to be the smallest value of this maximum flow limits. So if this condition is satisfied, we can say that our N2 region is safe, and here no any overload will occur. If this condition is failed, so we have to expand the N1 region to encompass the overload circuits. Further, we have expansion rule. It is the same as we discussed earlier. All the circuit N2 are safe from overload if the value of upper limit defined by the difference in the change of their angle is less than the smallest value of the bias line flow over all the line pairs of PQ. This is equation for this safe N2 region. If this condition is satisfied, then we can say that our N2 region is safe. If this condition is failed, or we can say if it maybe appears in this form, here we have less than or here we have greater than. So we can say if this condition is occur, so we can say here we'll apply the expansion rule. In this rule, we have to expand N1 and N3 to cover the violation. And we'll move to the second step, which is to calculate the new upper limits for N region 3, and we'll rerun the test over the newly defined region of N2. So this is bounding technique, and to get the clear idea of bounding technique, we have an example of 6-bus system, and we'll study the outage of line 9, which is connected from bus 3 to bus 6. And here we have the complete data of this bus system. Here we have mega watt values. Here we have initial flow. Here we have maximum flow, and here we have the maximum flow times the reactance. So here we can see these all values are in per units with the base value of 100 megawatt. We'll use this table to solve this example. In this block diagram, you can see that here we have a 6-bus system, and here we have N1 and N3 region, which covers bus 3 and bus 6. Here, actually, the outage occur in the bus 3 to 6, so which is line 9, and this is the N2 region, which covers the remaining buses. Further, we'll find for the N3 region, find the maximum change in N3, and we'll examine the line 3 to 6, which is line 9. Firstly, we'll find the change in theta 3, and here we have the formula for this. Here we need reactance from 3 to 6. We'll get from this table. Here we have 0.1. I think 0.1, and for x3 to 3, we'll get this value from this matrix, X matrix from 3 to 3. Here we will get this value 0.16590, and we'll get this power value from 3 to 6 from the same table here, 0.449. Okay. So firstly, we'll solve for theta 3, change in theta 3, which is 0.0577. Same for the theta 6. So we'll get the minus 0.0536. And then we'll find their difference, which is 0.1113. Now we'll compare this value, and we'll get the smallest value of maximum flow from the table. Here we have chosen 0.0075, which is the smallest value of maximum change, and which this is from line 2 to 4. You can see from this table here. Now this is the maximum flow line 2, and we'll select this value because this is the smallest value. Now we'll compare it. Here we can say this our value is is less than this maximum phase change. So here we can say this our criteria is failed, and we need to expand region N3. Here you can say we have expanded the region N3, and it covers bus 2 and bus 5. So further we'll move to step B, and in step B we have to find the maximum change N3, and line 2 to 5 will be examined. And here we'll calculate the change in theta 2 and theta 5 and their difference. So by using the same values, we'll calculate their difference, and which is 0.003564. Now again we'll check for the violations. Again the same smallest value of the biasful line is 0.0075 for line 2 to 4, which is greater than this maximum change of phase difference. Here our criteria is satisfied, so we'll further study about the N1 and 2 and 3 region where any overload may occur. Now in this slide, by using D factor, distribution shift factor, we can find the all flow in different lines, in all lines, when any outage occur in line 3 to 6. And here we can see that there exists overloads in 3 lines, line 2 to 3, line 2 to 6, and line 3 to 5. Here we can see here are overloads, and these all are these all lines are included in this region. 2 to 3, 2 to 6, 2 to 6 and 3 to 5. So these all lines included in the boundary region of N1 and N3. So that's all from my side. If you have any question, you may ask.
Hi guys, any questions for this presentation or for this part?
No, 老师。
Okay. Today's presentation is a good presentation. Everyone gives a very clear explanation, and some guys also give some examples and very explains the concepts, and also shows the result very clear. So I think you understand this part very well. Okay, it's in general it's a wonderful presentation. Okay. So that's for the presentation. So for the final project, I see some students still haven't chosen your topic. Please hurry up to fill your name in the table. Okay. In previous class, for the dynamic programming, the group wants to do this task independently. So I suggest the group 2, including the student Dario Sala, Mohammed Jamshed, Raman, Maizer Haq. And these 4 students, please choose another topic instead of the dynamic programming. Okay. I think you have. I think there are many topics you choose instead of the dynamic programming. For example, there are 3 topics about economic dispatch. I don't know why you guys not choose the 3rd project 3, and for economic dispatch. So it's very difficult for the project 3. I'm not sure. I think it's also a very easy topic. Okay, so for the dynamic programming, the second group, including Dario Sala, Mohammed Jamshed, Roman Manzer Haq, please choose another topic. Okay, if you have any more concerns, please contact me. Please contact me in person. Okay, by WeChat. Okay. So if you don't have any question, we will end our class. And please hurry up to fill the table for your final project. Okay. So if you don't have any more question, we will end our class today. Okay.
Thank you, Rahul.
Okay, Laushi.
Okay.
老师。
Okay.
Thank you.
Okay. Bye bye. Thank you all.
再见。